I think we should look at an example of Young's double slit. Let's consider light of wavelength 700 nanometers. That would mean this distance right here between peaks is 700 nanometers apart, shines through a double slit whose holes are 200 nanometers wide. That means from here to there is 200 nanometers, and they're spaced 1300 nanometers apart. That means from the center of one to the center of the other is 1300 nanometers. If a screen is placed 3 meters away, here's our screen, and it is 3 meters away, then what would be the distance from the central bright spot on the screen to the next bright spot? The central bright spot's going to be, well, it's in the center. You can follow this line. Look at it. It's kind of like a shadowy line right there. There's our bright spot, constructive point. How far would it be from that point vertically to our next one? Our next one's right here. You can see these lines of constructive interference. This one's about right here. So the question is, how far is this distance right here? How do we figure this out? Well, we're going to use the equation we found, which is to say that d sine theta, remember this is the formula right here, d sine theta is the path length difference. That's supposed to equal m lambda. Sometimes you'll see this as n lambda, but n reminds me of index over fraction, which confuses me, so I'm going to write it as m. Alright, so what do we do? D. What is D? We got all these numbers in here. D is defined to be the distance between the holes. So D in this case is this 1300 nanometers. So I've got 1300 nanometers times the sine of an angle. What angle are we going to talk about? Well, what we want to know is the distance, this distance here. So I'm going to worry about this angle. I'm going to worry about the angle from, here's my center line, from there to the point I'm concerned with is this first bright spot past the center point. So that's the angle I'm concerned with, this angle right here. Equals m. What should m be? Well, this is 0. Should I put 0? No, because I don't want the angle to the center one. I want the angle to the first one over here. So this is m equals 1, the first order bright spot constructive point, times the wavelength. What's the wavelength? The wavelength of the light, we said, was 700 nanometers. Now you might be wondering, wait a minute, what about this 200 nanometer wide piece of information? Do we have to use that? No, we don't. In fact, that does not play into here. The only time that this spacing is important, it's not going to change your calculation. You just need the spacing to be small. Small enough that you get enough diffraction, that you get a wide enough angle of diffraction that these two waves will overlap significantly enough that they'll create the interference pattern that you want to see over here to a degree that's visible. Okay, but we don't need it. We don't even have to use that one in our calculation. Alright, so we calculate the angle. Here we go. So I'm going to find sine of theta, and I'll get that sine of theta equals, 1 is just 1, so I divide both sides by 1300. I get 700 over 1300. The nanometers cancels nanometers. As long as I'm in the same units, it doesn't matter. I'll solve this for theta. How do I get theta? I've got to use inverse sine of both sides. So the inverse sine of sine theta is just theta, and the inverse sine of this side gives me 32.6 degrees. That's what this angle is right here, 32.6 degrees, but that's not what I was trying to find. What I'm trying to find is this distance, not this angle. So how do we do that? Well, this side right here, I'm going to call it delta y because it looks like it's a vertical distance. This is the opposite side to that angle. That's the opposite side. We know the adjacent side. This adjacent side, we were told, was 3 meters away from the screen. Or 3 meters. The screen was 3 meters away from the double slit. And how do we relate the opposite side to the adjacent side? Shoot, I know how to do that. Tangent theta equals opposite over adjacent. And our opposite is delta y over 3 meters in this case. So if I solve this for delta y, I'm going to get delta y equals, multiply both sides by 3 meters, times the tangent of theta. Theta we solved for right here, 32.6 degrees. And if you multiply all that out, you get 1.92. meters. That's how big this would be. From here, center point, to the next bright spot is 1.92 meters. That's how you solve this problem. You've got to use a little trigonometry. Once you get your angle, you've got to relate it to a distance vertically on the screen, and this is a common problem using Young's double slit. I will say one more thing. Oftentimes, a popular question, a follow-up question is, what would happen if we reduce the distance between the slits? What would happen if we take this distance between slits and we make it smaller? We scrunch these together. Would this angle get bigger or smaller? Well, mathematically, let's just look at it. If the distance over here goes down in our formula, if d goes down, notice I'm not changing the wavelength. That's determined by the laser I fire in here, and this wavelength's staying the same. So this whole side's got to stay the same because m is still 1 at this point. So what's got to happen to theta? If the d goes down and the whole thing has to remain the same, the angle's got to go up, because sine of a bigger angle will give me a bigger number. Sine of 0 is 0. Sine of something bigger than 0 gives me something bigger than 0, and the bigger the theta, the bigger sine theta. So as d decreases, sine theta's got to go up. That's mathematically why, but I can show you in here. Check this out. Let's just take this. Let's take this here, and I'm going to move this whole thing down and watch what happens. Can you see the shadowy lines spread out? See how they're spreading out? And then we come back together, and those shadowy lines of constructive, it's kind of ironic. They look like shadows, but they should be bright. It's just the way this visually looks. You get more and more lines this way. They get scrunched together, and as you push d closer together, as d gets smaller, they spread apart. These bright spots spread apart. So in other words, if I were to move these distances, these slits closer together, you would see these bright spots get farther and farther away from each other on the screen. So that's an application of Young's double slit. Good luck.